Alright, our next topic is homogeneous transformation matrices. And you'll often see these be called just transformation matrices. The name might sound a little bit scary, but they're really not too bad. It's mostly just kind of a fancy use of linear algebra. And they're not really related to sensing stuff, so we're kind of stepping away from sensing here towards the end. And they're more related to motion. But obviously I decided not to cover them early on in the motion part of the class. The reason is that I didn't really feel like we needed them to just look at basic path planning and basic control of a mobile robot. But really, transformation matrices are a very, very big part of robot motion in general. You've probably encountered them in the raw system without really knowing that that's what you're encountering. Uh, if you continue in robotics, you will almost certainly learn a lot about homogeneous transformation matrices, especially if you take the graduate level course. Like if you want to do like a early entry substitute in for undergrad credit, you can take intelligent robotics, and that's a graduate level course. It'll eventually be undergrad, but for now it's just grad. And in that course, you cover transformation matrices a lot. You start with them on like the very first day of class, and you really don't stop talking about them until the last day of class. So these are a very important topic in robotics in general, so I wanted to cover them. But the reason we're covering them right here at the end is because I didn't feel like they were necessary so far in what we had to do in this class. So we're going to cover them now. They will be on the last exam, and you won't really, but you won't really have like a normal assignment to do. Check Canvas for the assignment that you do have to do related to this. Okay, so what are they used for? So they're used to represent how two objects differ in Cartesian space regarding their position and orientation. So everything in Cartesian space, which is also Euclidean space, which you can just think of as the normal 3D space, everything is going to have a different position and a different orientation. And transformation matrices give us a way to represent this. So typically we have some world coordinate system. So here I drew this frame, and it's labeled as W, and it's a fixed frame. It's a fixed world coordinate system. And if we have some point out here in the space, we can represent that point with a vector, P, that describes how that point is represented with respect to the world coordinate system. So P is going to be the X component, the Y component, and the Z component. So this is what you've basically always used when thinking about points. You have some XYZ value. This is a bit more formal way to kind of show that. It's not that the point just magically has some value. It's that we have this vector that points from the origin from our coordinate system to that point. And that vector could be denoted as P here. So if our point was out there and had values 1, 2, 3, then that vector P would have components 1, 2, 3. And so for points, that's really all that we need. But, if we have an actual object in space, then we're going to need more information. So here we have this cube. It's labeled as B. And the problem is that the cube has a lot of points. In theory, it has infinitely many points that make up this cube. And we don't really want to have vectors pointing to each and every one of those points because, there could be infinite of them. So instead, what we do is we assign a frame to that object. So here I've drawn a frame, and I'm labeling it as N, and it has some X direction, Y direction, and Z direction. And those directions are aligned with the object. Not only the directions, but also the position is equal to some point on that object. So here what I've drawn is that the frame N, the origin of that frame, is in this back corner of the object B, and then the XYZ axes, they point in the direction of the of the cube's edges. And so if the cube moves around in space, then this frame is also going to move around with it. And it kind of gives us a way to efficiently represent this cube or this general object in space without having a bunch of vectors pointing to all the possible points. So this is nice, but it's not everything that we need. The reason is that what we really need is a way to represent this mathematically. So we can sit here and have this vector p that points to the origin of the new frame, and then we can find the angle values between the frame n axis and the frame w axis. So here I've drawn the difference in the y-axis as theta, so this here, and the difference in the z-axis as phi, and x, may have no difference here. So we can get all these values, but again, it's still just not really enough to actually use these values. So this is where transformation matrices kind of come to save the day, so to speak. So transformation matrices, they give us a way to represent one frame with respect to a different frame. So here in the top right, I've got this notation, big T, and N is on the bottom and W is on the top. And so what this means, how you would read this, is the transformation from frame N to frame W is equal to some matrix. And here I've got X, Y, Z, and P. These are all bolded, which means that these are all vectors. So they're not just single values, they are 3 by 1 vectors. And those vectors are going to be the unit vectors of the axis of N with respect to frame W. So when we want to represent this X vector here, this bolded X, if we come down here and we actually put in all the values, this column, excluding the 0, so just these 3 values, XX, XY, and XZ, all 3 of these values are going to make up one unit vector that describes how the X direction for frame N up here is pointed, but in terms of frame W. And similarly, we're going to do the same thing with Y. We're going to look at this Y direction, so how is Y pointed here? But try to describe how it's pointed in terms of W. Similarly, with Z, we would do the same thing. With P, we're just going to say, okay, what is the position vector to move from frame W to frame N? And with that, we mean the origin of frame W and the origin of frame N. So you can see over here on the left, we have this vector that's pointing from the origin of W up to the origin of N. Okay, so I think we should just jump straight into some examples here. I think that's the best way to really get a handle on what this means, because there's a lot of theory here, but when you actually look at them in practice, they're not too bad. So here's a first example where we have some world coordinate system W, and it's over here in blue. It's got X, Y, Z directions. And then we've got a cube here, and the cube is drawn in red. And the cube has a frame attached to it, and this frame is labeled as N. And so N has directions X, Y, Z. Each of those is parallel to W's X, Y, and Z. So this X parallel to this one, this Y parallel to this one, and Z parallel to ZW. And the origin of this frame is 0, 2, 0. So now what I want to know is, how do we fill out this matrix, this transformation matrix from N to W based on this information? So first, think about how would you describe X of N relative to X of W with the unit vector? So take a few moments and think about that. Okay, so just to give you the first one is going to be 1, 0, 0. And what that says is that to describe X of N relative to X of W, we would say that it's pointing entirely in the direction of X of W, 0 amount in the direction of Y, and 0 amount in the direction of Z. And that makes sense because these two x-axes are parallel, which means that they're never going to intersect, they're pointing in the same direction. So now think about Y. I'll give you a few moments. Probably best to just pause the video if you want to think about it. I'll give you about 5 seconds or so in video. Okay, so for Y, I'm going to get 0, 1, 0. And it's basically the same reason as we had for the x-axis. The two y-axes are parallel. So that means that this red y is going to be pointing entirely in the direction of the blue y. So we get this 1 here, and then 0 amount in X and 0 amount in Z. So now think about Z. So for Z, it's basically the same thing. It's pointing entirely in the direction of WZ. nothing in the direction of x, and nothing in the direction of y, which means that to describe that with a unit vector, you would get 0, 0, and 1. And so now lastly, think about p. What would p be? So p is kind of given to you. It's just 0, 2, 0. That means that the origin of n is going to be 0, 2, 0 points or units away from the origin of w. Okay, so now let's look at this other example. So here the cube has moved, so the position of the origin is no longer the same, and the axes have been flipped around a little bit. So think about how would you describe the x-axis of n, the red one, relative to w? So I would describe it as 0, -1, 0. What that means is that x is pointing entirely in the negative direction of y of w, that is. So it's not pointing in any direction in x, it's not pointing in any direction of z, it's pointing in the negative direction of y of w. So you get 0, -1, and 0. I also filled in the position for you, which should be pretty easy to figure out. It's just going to be -2, 0, 0. So now think about how would you describe y of n relative to w. And I can tell you that this y-axis is going to be parallel to the x one down here, and then this z-axis is parallel to this z-axis here. So think about how to describe y of n relative to w. Okay, so it should be 1, 0, 0. What that means is that the y of n is pointing entirely in the direction of x of w. It's not pointing in the other y of w direction. It's not pointing in the z of w direction. It's only pointing in x of w. So now think about z. Okay, so z is 0, 0, 1. That means that the z direction of n is pointing entirely in the z direction of w, and we know that because I said they were parallel, which means that they're pointing in the same direction. Okay, so now try this one. In this case, we have x of n is still parallel to x of w, but y of n is not parallel to anything, and z of n is not parallel to any of w's axes. So think about the first one. Think about x, and think about the position vector. What do you think those will be? So those are going to be 1, 0, 0 for the x direction. So basically saying that x is pointing in the same direction as x of w. And our position vector is back to being 0, 2, 0. Now think about the y direction. And so the y direction and the z direction are a little bit tricky because they're not parallel to these other ones. So we're not just going to have 1s and 0s. We're going to have some other values. So think about how would you make a unit vector that would describe the amount that this y value, y of n, is pointing in the direction of y of w, and how much it's pointing in the direction of z of w. Okay, so in order to do this, we have to go back to trigonometry. So we would kind of basically form a right angle here. So over here on the right, I've kind of pulled the z-axis over for you. And we have this red arrow here, which is y of n. And the bottom part, the horizontal part, is y of w. The vertical part is z of w. And if you look at it like this, you can tell, okay, they form a right angle. So now that we know that they form a right angle, how do we find the amount that's pointing in the y of w direction? Well, we just need to solve for a. And in order to solve for a, we can take cosine 45 degrees, which we know is going to be equal to adjacent over hypotenuse, and then solve for a, and we get cosine of 45 degrees. So our end result here is going to be 0, cosine of 45 degrees, and sine of 45 degrees. So the reason we get sine, let's just go back here, is that we're trying to find the vertical direction, and in order to do that, we're solving for O. And whatever O is, that's going to be in the direction of z of w. So when we have this unit vector here, we're going to have 0, cosine 45 degrees, and sine 45 degrees. And just to kind of test your intuition here, one thing I will ask is, what happened to our h here? So in the first part of the equation, we had cosine 45 is equal to a over h, and then we have a equals h times cosine 45 degrees, and then our h just goes away. So I just make sure you go over this and you can figure out why our h just kind of disappears, so to speak, here in this equation, because that will kind of show that you understand what's going on and understand how we're trying to devise these vectors. Okay, moving on. So for z, we're going to get something similar, a couple trig functions here. We're going to get 0 for x of w direction, negative sine 45 for the y component, and then cosine 45 for the z component. This one's a little less straightforward, so I made another little diagram down here. So we've got z of n pointing into the second quadrant, then we have y of w and z of w. I labeled the two edges of the triangle as y and z for like the axis, so this would be like the z of w, then y of w. So for the y component, we're going to get negative sine 45 degrees. So keep in mind this angle here is going to be 45 degrees, and the y component is opposite to the angle. So in the previous one, it was adjacent, but now it's opposite. So that means we need sine. So we have sine 45 degrees. And also keep in mind that the z vector, z of n, is pointing in the negative direction of y, w. So we have to tack on this negative sign here. So it's actually going to be negative sine 45 degrees. The z component is going to be adjacent to the angle, so we would just end up with cosine 45 degrees for that one. So this makes up the whole matrix. We have 1, 0, 0 for the x component because the two x-axes are aligned. For y, we get 0 cosine 45 sine 45. And then for z, we get 0 negative sine 45 cosine 45. And lastly, the position vector is 0, 2, 0. Okay, so now what we want to look at is how do we actually represent motion with these? How do we represent objects moving around in space? So there are two types of motion. There's translation, and that's when the origin of a frame changes, but the rotation stays the same. And there's rotation, which is kind of the inverse, and that's the origin of the frame stays the same, but the direction of the axes change. And so any type of motion that any objects do in space can be pretty much broken down into translation and rotation. So if we want to represent these with transformation matrices, we actually have special matrices for both types of motion. So the first one we'll look at is translation. This one's pretty simple. If we look at the rotation part, it's just an identity matrix, a 3 by 3 identity matrix. So this 1, 0, 0, 0, 1, 0, 0, 0, 1. What that means is that all of the axes are parallel to the other one's axes. So it's like saying that our x-axis is pointing in the direction of the parent x-axis, and the same for y and the same for z. And you can view that over here if we've got the n frame and everything is going to be parallel to the w frame. The thing that we have to look out for is what is the origin of n. And we're going to have to find some position vector pointing from w's origin over to n's origin, and that's what gets plugged in over here in this last column, px, py, pz. But so when you're trying to represent translation with the transformation matrix, you just have three values, three parameters that you need to be worried about, and that's px, py, pz, or just the components of the position vector. So if you can imagine, try to think about like grabbing this origin here and just pulling the frame all around and dragging it all around the space. The axes won't change, the directions of them, but only the position will. And then as you drag it around, these values over here in this last column are going to change in order to represent the translation from frame N over to frame W. Okay. So next we'll talk about rotation. Rotation is a bit more complicated, and the reason is that there are several different types of rotation. So just to recap, in rotation the frame rotates, but the origin remains the same. And so what that means mathematically is that these last columns over here are all going to be 0, 0, 0. As you can see, this one's 0, 0, 0, and then also here 0, 0, 0. And the middle part changes. So this first 3 by 3 matrix here, and this kind of like, not really the corner, but this part here is the rotation part, and these values are changing. And so if we want to rotate around z, so try to rotate around this axis z of w, we can rotate some amount theta. And to represent that, we would have cosine theta here, sine theta here, then negative sine theta in cosine theta. So notice that the values in the third row don't change. Those are all just 0, 0, 1. And the values in the third column don't change. Those are all 0, 0, 1, and then 0. So the reason is that this third column is basically like the z-axis, and so nothing's going to be changing relative to z. It's only changing relative to x and y. So those are the only ones that change. And so if we look at the x-axis, if we want to rotate around x, the first row and column don't change. It's the middle part that changes. And then here we have the same values, actually. Cosine, sine, negative sine, cosine. In y, we have the second row and column not changing. That kind of represents like the y directions. We have kind of the same values. We've got cosine, negative sine, sine, cosine. But really kind of what it is like horizontal, so like cosine, sine, and then negative sine, cosine. This one's a little weird. The y direction is a little weird, but essentially for all three of these, it's the same set of values. You've got 2 cosines, 2 sines, and one of the sines is negative. So that really helps me remember like how to fill in these matrices. But in general, if you have any of these matrices, they can represent rotation around one of the axes of some parent frame. And so that is very useful, but oftentimes we actually want to represent motion around some arbitrary axis. So if we have this black axis here, this black arrow just pointing straight through space, how would we represent rotating the obstacle around that? Well, the way that we do that is we just take rotations around z, y, and x and multiply those together. So we would take this black arrow here and decompose it into its directions along x, its direction along y, and its direction along z. We would compute how much the object would be rotating around those directions, and we would multiply the rotation matrices together, and we would get one really big matrix. So here, the C's represent sines, or sorry, the C's represent cosine, S's represent sine. And then each of the symbols corresponds to the rotation around a certain axis. So Z, we're rotating theta, Y, we're rotating psi, and X, we're rotating phi here. So if you take this fairly large matrix, well, actually the matrix is just 4 by 4 still, but the values inside are a lot more complicated than they were before. But if you take this and you can actually use it to multiply by some vector, and it'll represent the rotation of that vector along any arbitrary axis in space. And so that's actually really cool, because although this seems really complicated, like just looking at the values inside the matrix, at the end of the day, it's still just a 4 by 4 matrix, which means it's only 16 values. And in the world of computer science, 16 is an extremely small number. So if we can represent something, very complicated with only 16 numbers, that is very good for us. The alternatives that we kind of briefly skimmed over would be trying to rotate every single point, and we can have infinitely many points, and it just becomes a giant hassle. Here we can represent any rotation that an object can do in space with just 16 values, which is extremely efficient. So now you're probably wondering, do I need to memorize this? The answer is no, of course not. This is way too complicated to ask any person to memorize. So I would never ask you to reproduce this final matrix down here. But I wouldn't say that you're entirely off the hook here. What I would expect you to understand and to be able to reproduce is the top equation. So if I say I'm rotating, some theta, psi, and phi, I would expect you to be able to show me how do you build such a matrix? How do you multiply other rotation matrices in order to build a larger rotation matrix for some arbitrary axis? So keep in mind that order matters. So here we have z and y and x. That is not the same as doing x, y, and z. So typically we do it right to left. So here this actually represents rotating around x, then rotating around y, then rotating around z. And if you want, you can get really deep into spatial transformations like this. There are lots of different ways to form these matrices based on the type of motion you're doing. We're not going to cover that now, but just know that I wouldn't. And I don't think anybody else in the world would expect you to be able to reproduce all of these formulas down here for this final matrix, but it is important to understand how this final matrix is built. And the way that it's built is by decomposing an arbitrary axis into other axes that we know, x, y, and z of w, and then rotating around those axes and multiplying those rotations together. And that will give you some final rotation matrix that would represent some arbitrary axis in space. Okay, so getting towards the end here, if we want to build a final transformation matrix that represents both translation and rotation in the same matrix, what we do is we take the rotation part, which I'm not filling in all the values here because they were very long. But kind of imagine that big matrix you just looked at in the previous slide, and it would go here where we have this bolded R from A to B. This is the rotation matrix from A to B, and that's going to be a 3x3 matrix part. So keep in mind that the previous one was 4x4. Let me go back. That's because the position column over here was just 0, 0, 1. Really, the meat of this matrix is this 3x3 portion. And that 3x3 portion is going to go here where we have bolded R. And then over here on the right-hand side, the last column, we just have the position from A to B, and that's kind of like doing that translation matrix a few slides ago, where the rotation part was an identity matrix and the position vector changed. So if you stick those together into the same matrix, then you can do translation and rotation all in one matrix. So you're doing not just rotation or translation, but both, and you're doing both with only 16 numbers, which is pretty amazing. So I put down here just some ways to describe these transformations. So probably the most common way or the most technical way is the coordinate transformation of frame A to frame B. Another way that you could think of this or describe this is the location of the object at frame A with respect to frame B, or the relative motion of an object from frame B to frame A. So keep in mind this one down here is like reversed, and that's like saying we started at frame B and we're going to frame A. And I'm just realizing now these don't match up with Y and N. In this case, A would be equal to N and B would be equal to W. Okay, so I want to look at just a couple properties. The first one is the inverse property. So if I know the transformation from A to B, but I want to go the other way around, I want to get from B to A, the way that you do that is by taking the inverse of the transformation matrix. So very important to note that the inverse of a matrix is not going to be equal to just negating all the values. So the inverse of a matrix is a very specific property that if you just like put a negative sign in front of all the values, that does not actually give you the inverse. So I put the exact formula down here. So if we have the transformation from A to B, and that has some rotation component and it has some translation component, the way that we invert that is for the rotation part, we just take the transpose of that rotation matrix. So just recall linear algebra, we take the transpose of that. And then for the position part, we're going to take that transpose rotation matrix and multiply it by our position vector. And then we're going to end up with the rotation from B to A and the position from B to A, which of course is just equal to the transformation from B to A. So keep in mind, if you have one transformation, like in one direction, and you want to know the other direction, this is how you do it. So just keep in mind, you do not negate all the values. You have to take the inverse of the matrix, and that's a fairly specific property. Okay, the other one I want to look at is commonly referred to as the chain rule. So what if we had like 3 or more frames? So here we've got a world coordinate system that is A. We've got some objects B and C, and they each have frames attached to them. So what if I know T from C to B, so from the green frame to the red frame here, and the transformation from B to A, so the red frame to the blue frame. But what I really want to know is the the transformation of frame C with respect to A. So going from all the way out here to the world coordinate system down here, and totally bypassing B. So in order to do that, I just multiply the transformation matrices together. So I would take the transform from C to B, like here, multiply that by the transform from B to A, and that would actually give me the transform all the way from C all the way back down to A. And this is kind of the most general form of this this property. You might see it called the chain rule. You might just see it called the transformation equation. But if we have a bunch of transformations, say we have n of them, and we want to know the transformation from n all the way to 0, what we would do is just kind of chain them all together. So the transform from n to n minus 1, multiply that by the transform from n minus 1 to n minus 2, go all the way back down until we finally get to, t, the transform from 2 to 1, and then transform from 1 to 0. And that would give you the transform from n all the way back down to 0. Okay, so let's look at some more robot-specific examples. So here we've got the robot we've been using in class, the Turtlebot 2. And the Turtlebot 2 actually has a lot of frames associated with it. You may have noticed whenever you brought up RViz that there were a bunch of frames that popped up. If not, if you didn't notice it, then just know that it has a lot. So one of them is going to be the center of the mobile base, and I'm denoting that as B. And another one is going to be the center of the camera, or the center of the front of the camera. And we're going to denote that as C. So, we also have this object out here, O. And so if we want to move this robot from B to O, we need to know the transformation that we have to satisfy. So how do we find the transformation from O over to B? So we know the transform from C to O. That's because we can see the object with our camera. So if we can see the object with our camera, then we're going to know the transformation of the object to our camera. And we know the transformation from the camera to the base, and that's because that is something that is static and won't change. That's just part of the physical layout of the robot. So when you build a robot, you know that when I put the camera here, I can tell you what the transform from the camera to the middle of the base is. So we know those two things. How do we find the transformation from O to B? Well, that's just going to be using the chain rule. So we take our transform from O to C, and we multiply that by the transform from C to B, and then we would know the transform from O to B. And then we can say, okay, that's the transform that we have to get our frames into. Now we can start moving our robot to satisfy that. So what if we put a gripper on this guy? So we have this little arm that's sticking out here, and the gripper has some center, and I put a frame on it. It's denoted as G. And what if we want to, have this gripper pick up this object over here? So the things that we know T from O to C, that's something from last time. And we know T from G to C, that's going to be, we can see it with our camera. The transform from G to B, that's going to be part of the physical layout of the robot. We'll be able to compute that. Even though the arm will be moving around, we can still compute it. And the transform from C to B, which is part of the physical layout of the robot. So given all these transforms, what we want to know is how do we get the transform from how do we get the transform that we need in order to pick up the object? So my first question to you is, what is the transform that we're actually looking for? So the transform that we're looking for is from O to G. Right, so if we want to get our gripper here, if we want to know what the transform needs to be from the object to the gripper. And so now my question is, how do we find that? Okay, so this is going to be the full equation to find that. So we're going to take the transform that we know from O to C, so how we see the object from our camera. And then, well, we have T from G to C, but we want the opposite of that, so we're going to invert that. And whenever we invert that, it comes over here, and it changes to transform from C to G. And so if we look at the right-hand side here now, this should satisfy the chain rule that we looked at, so we would eventually get the transform from O to G. Okay, so just to recap, transformation matrices allow us to convert coordinates from one frame to another frame, and it's done in a pretty efficient and intuitive way, and we can represent basically any motion in 3D space with these matrices. This comes into play in robotics a lot, but not so much in mobile robots, more in robot arms and robot manipulation. So, there are lots of robots in the world that try to move things around and try to build cars and do things like that. For those robots, transformations are a really big deal. For mobile robots, they're important to a certain degree, but they're not a central focus like they are in robot manipulators. So we're covering them here now. You should make sure that you have a brief understanding of these. Information from this will be on the final exam. So make sure you have a fairly broad understanding, not super technical, but good enough to answer some basic questions. If you want to know more about this, you can look into Euler angles. So that's actually what we did here, but just a variant of it. There's a lot of information here if you want to go do some self-study. And then lastly, quaternions. So quaternions are kind of like an alternative approach to represent rotation in space. If you get into the gaming world, you will use quaternions more often. And quaternions are something that you all have used here in the class. Okay, that's all I have on this. If you have questions, please email me or come by office hours, or just try to get a hold of me in general.